What's up, guys? So today we're going to discuss about one of the bases for our internet and how we are able to access the internet so fast, that is Content Delivery Network, CDN. You must have heard about this word a lot. Today we will deep dive about it. When Netflix was serving everything from a single data center in Virginia, a user in Tokyo waited 220 milliseconds for every HTTP request, not 220 millisecond for the video, 220 millisecond for every segment, every image, and every script. That adds up. Buffering, dropped frames, users cancel. The problem wasn't serving capacity or bandwidth, it was basic physics. Light travels roughly 20,000 kilometers in 67 seconds. You cannot make Virginia closer to Tokyo, but you can put a server in Tokyo. Now that's the entire idea about CDN. Move the content close to the users. CDNs now handle 70% of all the internet traffic. Let's look at how they are designed. Think of a library system across a country. The national library in the capital, your origin server, has everything. But there was local branches in every city, your edge servers, with the curated selections of popular title. When you walk into the local branch, you check the local shelf first. You found it? Done in 2 minutes. Not there. They requested from the regional warehouse. Still not there. It comes from the national library. Meanwhile, the popular book stays at your local branch permanently. Here are some of the functional requirements about what the CDN must do. It should cache static content like images, CSS, JS, videos with a TTL. It should route the users to the nearest edge like the GeoDNS or using Anycast, fetch from the origin or cache misses. It should do cache invalidation, then it should do content transformation, it should compress it, resize the images, adaptive videos. Another most important is HTTPS termination. Then analytics. It should analyze the cache hit ratios, the bandwidth, the latency per edge. One of the interview trap is the interviewer asks you what's the difference between push and pull CDN. Pull CDN fetches on first request. Push CDN preloads the content. Most CDNs are pull based. Know when to use each. Now let's jump onto some of the non-functional requirement. Here is the description about the non-functional requirement. There are around 10 billion requests per day. So it means it will be around 115,000 RPS average. At peaks, if it is 3x average, then it will be 350,000 RPS. The average object size is around 500 KB. So 115K into 500 KB is 460 Gbps average bandwidth. At peak, 1.4 Tbps, 200 HPOPs into 500 GB cache is equal to 100 TB total edge cache capacity. Now, 1.4 terabytes per second of peak bandwidth. The origin server should never see most of this. That's the point. If your CDN is working correctly, your origin receives 3 to 5% of the total traffic. If it's receiving more, then something is wrong with your caching configuration. Here are some of the non-functional requirements. The cache hit ratio should be 95% plus. Only 5% requests reach the origin. P99 should be lesser than 50 milliseconds for the cache content. Edge with 30 milliseconds of 95% for the user. The availability should be 4 nines. CDN failure will lead to entire website down. Then the purge propagation should be less than 5 seconds across all 200 plus edge nodes. The throughput, millions of RPS globally. Cache hit ratio is the single most important CDN metric. Below 80%, your origin is absorbing too much load. Below 60%, you may as well not have a CDN itself. Alright, now comes the main part, that is the high level design. We'll discuss about each of the components. There are 4 tiers and each adding a layer of caching between the users and the origin. The first one is the edge layer. It is closest to the user, 200 plus points of presence globally. In major metros, New York, London, Tokyo, Singapore, Sao Paulo, each POP has multiple servers behind a local load balancer. Then the mid tier, the regional cache, shared across edge POPs in one region. When the Tokyo edge misses it, it asks the regional Asia cache before going all the way to the origin. This caches 12 to 15% of the traffic that edges miss. The origin shield, one cache layer directly in front of your origin server. All mid-tier misses from all the regions funnel through here. And here's the important feature: request coalescing. If 50 edge nodes all miss the same object simultaneously, only one request goes to the origin. The other 49 wait for the first response and then all get served from it. Then origin, your actual server, Nginx, S3, whatever, should receive only 3 to 5% of the total traffic. If it's receiving more, your CDN isn't working. Then we have the control plane. Separate from the data part, it handles configuration, pushes, purges, commands, health checks, analytics, never touches the request layer. Let's go a bit deep dive. Let's go at the lower level. Here are API and data model. The CDN API at the user facing level is just an HTTPS request. What matters is the response header. Here is a GET API which requests for a image and the host information. The response headers create has X cache, then XH location, then cache control, then E tag, and the age. These headers tells you everything about the cache behavior. For example, S cache hit, it means the edge added. The age 3600 means it's been cached for an hour. Check these headers in the Chrome DevTools for any CDN served asset. You'll immediately see the cache behavior. There's one API which we'll be discussing is the Purge API. So here's the post request. This contains the headers of authorization, then the URL, and then the target CDN. The response is per the Purge ID, the status, edges target, and the estimated completion seconds. After this, we'll discuss one of the major table, that is the cache table. Here the fields are cache key, it's a primary key. Then we'll have the content hash, it's the hash of the content. It's the content type, tells which type of content, it can be JPG, image, or video. Then the TTL seconds, it is the time to live. How long will it survive, after how long it will be deleted. Then we have the expires at, the expiry time, the last access time. It's the name is self-explanatory here. Then the access count, then edge location, and the status. All these fields are self-explanatory, so I don't need to explain all of them one by one, just giving you a brief about it. Then we have created an index. The index is IDX expires on the cached object. Cache control is the contract between your origin and the CDN. Max age 3600, caches for 1 hour, then no cache forces revalidation on every request. State while revalidate is equal to 60 serves the stale content while fetching fresh in the background. S max age is equal to 86400 overrides for the shared caches like CDN even when the browser cache is shorter. Get these headers wrong and you either serve the stale content to the user or hammer your origin unnecessarily. Alright, now we'll go dive deeper into the design. So here are some of the concepts which we are using in this system. First concept is multi-tier cache hierarchy. The edge alone gets you roughly around 80% cache hit rate. Add mid-tier and you can catch 80% of what the edges missed. That gets you to about 96%. Add origin shield and the remaining 4% gets coalesced, so most origin requests never actually happen. Why not store everything at the edge? It's the storage cost. Edge nodes are co-located globally in expensive rack space. 2 TB per edge node times 200 POPs equal to around 400 terabytes. Mid-tier and origin shields are centralized, 50 TB total, 8x C per byte. The next concept is the cache invalidation. This is the hardest problem. You update your home page hero image. How do we ensure all the 200 edge nodes stop serving the old version within seconds? There are 4 strategies, and the best one even might surprise you. First one is TTL expiration. Set cache control max age is equal to 3600 and wait. It's simple but stale for up to 1 hour after update. Then the Purge API. Post to purge, the control plane fans out delete to all the edges. Edges drop the cached object. The target is 5 seconds global propagation. Then we can have version URL. We don't use simply hero.jpg. We update the image by hero.v2.jpg. Here we are adding the version. New file, new URL are guaranteed cache miss. Old URL expires naturally. Zero coordination needed. This is the best approach for static assets. Then stale while revalidate. Edge serves stale content immediately while fetching fresh copy in the background. User gets the speed. Content stays fresh within the window. The third concept we are going to deep dive now is the request coalescing at origin shield. This one is very important and we need to make sure we have this. The origin shield receives around 50 simultaneous requests for the same uncached object. Now, without coalescing, 50 origin requests arrive at once. Origin gets overwhelmed. With coalescing, first request goes to the origin, then the 49 others wait behind per URL mutex. When the origin responds, all the 50 get served from that single fetch. The coalescing window is typically around 30 seconds. If the origin takes longer, additional requests are forwarded. You never block indefinitely. But in practice, coalescing prevents most thundering herd scenarios at CDN layer before they ever reach your infrastructure. Okay, now we are going to discuss a part which is also very important along with the design. If not taken, then you might be rejected at a staff level or a senior level, and that is the observability. Here are some of the panels which we can use. One is the cache hit ratio per POP. Then it should be greater than 90% everywhere. Then we have origin requests per second. It should be less than 5% of the total. And in panel 3, we can have purge propagation latency. That is a histogram. It tells how long to reach all the edges. It has an SLA of around 5 seconds. 95% should be less than 3 seconds. Track cache hit ratio daily per POP. A healthy CDN has around 90% plus everywhere. If one POP drops to 70%, then investigate it, possibly a misconfigured TTL or unusual access pattern for that region. The origin storm pattern, cache hit ratio drops, origin spikes simultaneously. Almost always means a deployment reset cache keys or mass TTL expiration. Now, these design does have some failure points and it's a must. If your design does not has a failure point, then you're not a good architect. You should know what are some of the failures. And that's very important. First failure could be an edge node goes down. For example, the Tokyo edge crashes. The DNS health check detects failures within 30 seconds. DNS stops returning Tokyo's IP. Traffic now reroutes from Osaka, the next nearest node. Users experience slightly higher latency, 20 milliseconds instead of 12 milliseconds, but no downtime. The fix for this is active health check every 10 seconds. Passive error rates monitoring. If an edge returns 5xx on more than 1% of the request, remove that from rotation immediately without waiting for the health check cycle. And then put a circuit breaker at a DNS layer. The second failure that could happen is the origin overload or a cache miss storm. Suppose a product is launched. The new content is pushed to the CDN. 10 million users hit the CDN simultaneously before any edge has cached everything. All cache misses. The origin receives 10 million requests in 10 seconds. Origin is now overwhelmed and returns 503s. The CDN marks origin unavailable and serves 503 to the user. Now, this is a bad experience. There are three fixes in sequence we need to do in this case. First is origin shield coalescing. This prevents most of it. Stale while revalidate. Serve slightly old content when the origin returns errors rather than propagating the error to the user. We could pre-warm the CDN by pushing the popular content before launch. The next failure is cache poisoning. If an attacker sends a malicious request whose response contains cache control max says 86400, the CDN caches the poisoned response. For the next 24 hours, everyone gets the attacker's content. Now, the fix for this is validate origin responses before caching. Never cache responses with headers injected by the client. Validate the cache control values that are within the expected range. Reject 5xx responses from being cached. Strip the client's applied or host headers that could affect the cache keys. Security headers, like content security policy in origin responses, provide a secondary defense layer. Now, after all the failures, here are some of the improvements we can do to our design at the next level. First is Anycast routing. This is more accurate than GeoDNS. Now, GeoDNS looks at the user's DNS resolver IP. If a user in Tokyo uses Google's public DNS based in the US, the GeoDNS routes them to the US edge. This is a wrong continent. Anycast solves this. All edge nodes advertise the same IP URL via BGP, and the internet routing naturally directs the packets to the topological nearest node. Cloudflare uses Anycast for all the routings. Automatic failovers without DNS changes. If an edge node disappears from the BGP, packets route to the next closest automatically. The second is HTTP3, that is QIC. It is for faster connection. HTTP2 over TLS requires 2 to 3 round trip to establish a connection. That is around 150 milliseconds before any data flow on a first request. The HTTP3 over QIC does 0 to 1 round trips because TLS is built into the protocol. Mobile networks with 2 to 5% packet loss, QIC is 30% faster than TCP because it handles packet loss at the protocol layer more efficiently. Deploy at the edge layer only. No changes to the origin. Users on modern browser get it automatically. The third improvement which we can do is the edge compute by moving the logic to the edge. Traditional CDN only serves static files. Dynamic API's calls go to the origin. The edge compute lets you run JavaScript or WebAssembly code directly at the edge node. Cloudflare workers fastly compute this. Use cases like A/B test variant selection, the authentication token validation, personalization, header injection, all without a round trip to origin. This reduces the origin load 30 to 50% for dynamic applications and dramatically reduces API latency for users far away from the origin. Okay, so these were some of the improvement, but latency is physics. You cannot make Virginia closer to Tokyo. What you can do is put a server in Tokyo, cache the content there, and serve it locally. That's the only way to serve a global audience at an acceptable latency. Remember the numbers. 95% cache hit ratio means 95% of the requests never touch your origin. Multi-tier caching, edge, regional, origin shield compounds these savings. Three things to take away here is the cache hit ratio is your health metric. Below 90% investigated. Version URLs beat the purged APIs for the cache invalidation. Zero coordination, instant effect. Origin shield plus request coalescing protects your origin from its own content going viral. Move the content to the users, then everything else follows that. Till then, see you in the next one.